Hello students, now we enter chapter 21. The topic is mass spectrometry. This technique has been widely applied to determine the unknown molecules, okay, and also to determine the molecular structure. Okay? This is a really popular technique, and several Nobel prizes were awarded to the development of mass spectrometry. Okay, let's start. Our front page shows droplet electrospray. Okay. This one here uh, from this container, um, the acetone, okay, uh, falling down drop by drop, whose diameter is about 16 micrometers. Okay, very small uh, drops of acetone falling down. But now let's assume you apply very high voltage, 6,000 volt from our this one, this container, and here the platinum wire, very small tip. Okay, and under this high voltage, this acetone droplets now positively charged. Okay, high voltage creates here a glowing electric coronal discharge. Okay, yeah, under this very high uh, potential difference, the plasma um, uh, is produced. So this plasma now, this coronal discharge now what makes this acetone droplet positively charged. Okay, um, and the droplets falling through the discharge. Yeah? But here discharge is not visible in this photograph. Yeah? Anyway, the droplets are positively charged, and since this platinum wire is also positively charged because it is high voltage. This is the negative terminal and this is the positive terminal. So platinum wire is also positively charged. So these droplets, when it uh, is close to this platinum wire, positive and positive the charged things are repelled each other. Okay, so this one droplets are repelled. And one method for expelling charged protein molecules into the gas phase for mass spectrometry is called electrospray. Yeah, this technique is called electrospray. Yeah? And this electrospray is uh, one method to ionize the molecules. Okay, this is an example, and this one electrospray has been well applied to the molecular weight determination for large molecules like proteins. Okay, well the mass spectrometry has been invented by this Francis W. Aston. Okay, he was a I think the Englishman, and he was a professor at I think Cambridge University. He developed mass spectrographs in 1919. Okay, and he developed a way to separate ions differing in mass by 1%. Okay, at the time 1% is small, but you know, from today's standard, this 1% is nothing, right? Yeah, we can do it much better. Okay, and focus them onto the photographic plate. Okay, well, it's a long time ago, more than 100 years ago. Okay, so Aston immediately found that neon consists of two isotopes. Okay, by the time the neon isotopes was not known. Okay, but by separating the mass, okay, he could identify the neon isotope. Okay, and went on to discover 212 of the 281 naturally occurring isotopes. Okay, wow, it's amazing. Using this technique, he could discover this many isotopes out of 281, yeah, naturally occurring isotopes. Okay, he so almost identified every you know isotopes. Okay, by this work, he received the Nobel Prize for Chemistry in 1922. Okay, yeah, this is how mass spectrometry started. Okay, and by the way, what is mass spectrometry? Hmm? To apply mass spectrometry, you have to ionize your species. Okay? Usually molecules. Okay, the molecules should be positively charged or negatively charged. Otherwise, the mass cannot be determined. Okay, look at this mass spectrum. Okay, it is all, let me see, all about lead. Okay, and lead, let me see, there are one, two, three, four peaks. Okay, this is a mass spectrum showing natural isotopes of lead observed as an impurity in brass. Okay, brass is alloy. It contains a small amount of lead, but using mass spectrometry, one could identify at least four different isotopes. Okay, this one is mass number 204, and this one 206, okay, and 207, 208. Okay, yeah, this peak area is proportional to the abundance of the of this species. Okay, and as you see, there is this peak. Okay, it has a peak width. Okay, and gaseous species are dissolved from condensed phase and ionized. Okay, ionized must be ionized. The ions are accelerated by an electric field and then separated by many means according to their mass to charge ratio. This one m over z. This is very important. Okay, yeah. So since we know the lead atomic weight is around 206 or 7 or 8, right? And we can immediately know this lead is this ionized, right? And then the charge is plus 1, okay? Because m over z, z is a charge, m is a mass, okay? So actually these numbers are atomic numbers, okay? So, as I said, the area of each peak is proportional to the abundance of each isotope. Okay. Yeah, this is one of the mass spectrometer structure. Okay. First, in the molecules should be ionized and in gas phase. Okay, it must be in a gas phase. So gaseous molecules are converted into ions. Okay, look at that. Here you inject your sample here from this part. And then now sample is moving down, and then it passes through this magnet. Yeah, in the magnet, its path is bent. Okay, and then it's detected by here this electron multiplier detector. Okay, and but how do we ionize these gaseous molecules? There must be a way, yeah, to ionize. Okay, here, the neutral molecules are what input from this side, and there is a electron beam here. Okay, you see, it's electron beam. So now neutral molecules now pass through the electron beam, and the molecules are ionized or fragmented. Okay, either. Okay, and then now ionized this molecules or fragments now pass through this. Let me see here. This plate, and then here some voltage is applied, okay, and then this ionized species now accelerated, yeah? And then these ions are moving down, okay, and then here when it enters this magnet, you, know, you see the charged particles, the pass, it becomes changed, right, in magnet, okay. Here, depending on the magnetic field and mass to charge ratio, okay, and then also and then here accelerated voltage, okay. It is not very clear here, so this it what this linear path now becomes in a circular path, okay. And then here, depending on the some variables, only selected mass to charge species enters this a detector, okay. And usually, electron multiplier detector is used, yeah? But this is one of the several detectors, okay. Now ions, of a specific mass to charge ions now enters the slit, and then it hits the detector cathode, okay, and then electrons are ejected from this cathode, okay, and then this electrons are attracted to this diode, and then uh, these electrons are multiplied. For example, one electron hit the diode and two electrons are produced, and like that. And the principle is the same as photo multiplier tube, okay. And then here, um, finally the all the electrons are collected at the anode, okay. And then electron flow is what? That's current. So we can measure the current, okay. And usually, ions usually positively charged ions are detected, okay. But depending on how we ionized the species, negative ions may be produced, okay. In this case, the voltage should be reversed, okay. Mass spectrometers can measure negative ions, but that is not a usual case, rather unusual case, by reversing voltages where the ions are formed and detected, okay. So negative ions could be detected, but usually positive ions are detected, okay. To detect negative ions, a conversion diode with a positive potential is placed, okay. To detect negative ions, so this diode must be positively biased, okay, to detect uh, what the positive ions, but these diodes are negatively biased, okay. Yeah, this way, this is the one of the mass spectrometers, okay. There are several different types of mass spectrometers, right? Okay, but before going into details, let's first distinguish molecular mass and nominal mass. All right, atomic mass is the weighted average of masses of the isotopes of an element. Uh, in every chemistry textbook, uh, usually on the front cover, there is a periodic table, and periodic table gives many information, especially for every element. It gives a atomic mass, okay. But what is the atomic mass? For example, bromine. Yeah? Bromine atomic mass it says in a periodic table says 79.904 Dalton. Yeah? But actually, bromine has at least two isotopes, mass number 79 and mass number 81. Okay, and the mass number the 79, but this is not exact number. Exact number is 78.91834. Okay, but usually in this notation, we put the integer number. Okay, and this mass number bromine atom takes 50.69%, and mass number 81, okay, actually is exact mass is given here. It takes 49.31%. Okay, so when we take bromine atoms, and then you know it contains um, these two isotopes. Okay, so when we say atomic mass, we usually say the average atomic weight. Okay, and 0. Or this percentage. Okay, 5069 multiplied by this atomic mass plus this abundance 0.4931 times this mass number gives 79.904 Dalton. Okay, atomic mass. This is the atomic mass of bromine. But in mass spectrometry, we can differentiate every single isotopes. Okay, so uh, we so in mass spectrometry, we we could we could separate all the isotopes. Okay, we can have a very exact atomic mass. Okay? Here, Dalton is usually used in biochemistry. The unit of atomic mass is Dalton, Da, defined as 1/12 of mass of carbon 12. Okay, mass number 12. This is definition. All right. So we cannot argue against this. Okay. So mass spectrometrists prefer U rather than Dalton. Okay, U uh, for unified atomic mass unit. Okay, usually AMU, but for this mass spectrometry, people prefer U. Okay, Da, Dalton, and U are synonymous. Okay, can be used interchangeably. The molecular mass of a molecule or an ion is the sum of atomic masses listed in the periodic table. It's very simple. Okay, for the bromoethane, okay, here C2H5Br. So molecular mass is given by the sum of the atomic masses. Okay, and now it's 108.965. Okay, but now you have to be careful for the nominal mass. Nominal mass of molecules or ion is the integer mass of the species with the most abundant isotope, okay, of each of the constituent atoms. All right. So for this the molecule, okay, so nominal mass is what? If this molecule, if each atom uh, has only isotope C12, H1, and bromine 79. Okay, and then you simply add only the integer these numbers. Okay, so the nominal mass of this uh, bromoethane is 108. Okay, but if this contains only mass number 81, okay, and bromine, and then this mass number will be increased to 110. Okay, so you have to differentiate the molecular mass and nominal mass. Okay, and then we saw this magnet uh, the magnet based mass spectrometer. Let's consider the principle how ions of different masses are separated in a magnetic field. Okay, when ions or any charged particles enters in the magnetic field and then because of this magnetic force, uh, that charged species, makes a circular motion, okay, inside the magnetic field here. And uh, here is an charged particles, okay. Here the magnetic field B now goes into the page, okay, into the page. That means it uh, applies the perpendicular to this screen, all right. And then force is acting toward the center, okay. You see the magnetic field is applied there, into the page. And now this velocity is a v, okay. They are all vectors, okay. And then this one, the kinetic energy of charged species equals this one, z and ev. Z means what? This charged particle, charge number, and ev is the potential energy. Yeah, this potential energy uh, is obtained in the in this uh, here, because the ions are accelerated by the potential difference. Yeah, so people usually apply the potential. Okay, and from this equation, this velocity is given by this simple equation. And then since it makes a circular motion, okay, and then here uh, this equation uh, could be satisfied, okay. This is from electromagnetic theory. And then the velocity here is given by this one, okay. And then these two velocities must be equal, and here we get mass to charge. The ratio is given by electron charge and magnetic field intensity squared, and this one, this trajectory radius squared divided by 2, and voltage, acceleration voltage, okay. Here I'll explain again. An ion with charge Ze and velocity v traveling perpendicular to a magnetic field, okay. This one, this direction and magnetic field direction is perpendicular, okay. uh, and the ions experience a force. This force, magnitude is this one, right? That is perpendicular to both the velocity vector and the magnetic field vector. Okay, this force is both is perpendicular to this velocity and magnetic field. Here r is the radius, okay, or curvature. This one is the here this magnet curvature, okay. So this r is fixed. Ions can be selected to reach the detector by adjusting uh, the magnetic field intensity or the accelerating voltage V, okay, although it is not given here, okay. Yeah, that's the principle. And let's stop temporarily here.